Welcome to lecture 20 of Power System Protection course. In the last lecture, that is lecture number 19, we discussed about the differential protection schemes, and we have seen how the external faults affect the stability of the differential protection scheme. And we defined the through fault stability by quantifying through a term that is called stability ratio. And therefore the percentage differential relay came into picture, percentage bias differential relay, by which in fact the relay characteristic has been improved, has been modified with a slope, and by that way the through fault stability has been improved. It is improved by improving the stability ratio. So already we talked about this, and in this lecture we will talk about transformer protection. So before that, let us see a little bit the differential protection, because differential protection plays very important role in case of transformer protection. So already we know this. This is your spill current I1 minus I2, which is equal to K times I1 plus I2 by 2. This is your circulating current I1 plus I2 by 2, and K is your slope of the, so K is defined here as NR by NO. NR is the number of turns in the restraining coil, and NO is the number of turns in the operating coil. However, if we take into account the effect of control spring, the above equation can be written in this form. KO represents the effect of the spring torque. Okay. So where K0 accounts for the effect of spring. Now already we discussed this, and this is your relay characteristic, right? Percentage differential relay characteristic with 25% slope, and this is your internal fault characteristic. Already we discussed how it came 200% the slope. And now the relay characteristic can be changed by changing the number of turns in restraining and the operating coil. So here it is taken 25%, and therefore the maximum through fault current has been improved, has been increased in fact to this value. And already we discussed how the stability ratio improved in fact, right? So all these things we have discussed, how this came in, the slope of the internal fault characteristic became 200%, right? It is because your spill current is I1 and circulating current is I1 by 2, so it will, the slope will become I1 by 2, so therefore it is equal to 2. This is 200%, right? And your stability ratio also, it improves as compared to the simple differential relay characteristic. This parallel line is your simple differential relay characteristic, this dotted line, right? And in fact this is intersecting at this point. So when for a simple differential relay characteristic, for simple differential relay, your through fault current is less as compared to the through fault current which is observed in case of percentage differential relay, right? That is here. So it is greater as compared to the simple differential relay. Therefore your stability ratio has been improved. It is because it is the ratio of IF max external to IF minimum internal. So IF minimum internal is not changing much. It is very less difference as compared to the simple differential relay. It is approximately remaining same, and therefore your external IF maximum external is increasing by improving the stability ratio. So therefore your stability is improving, stability of the protection scheme is improving, right? So this is all about your differential relay. Now we'll talk about transformer protection, where the differential relay in fact plays very important role. So differential relay plays very important role in case of transformer and also in case of bus bar, for bus bar protection. So before moving ahead, let us see different types of transformers. So already we have studied in your last courses these things. One type of the transformer is called generator transformer, which is used in the generating substations, right? So generating substations, what is the function of this? This in fact steps off the voltage level which is at the generator. Generally at the generator the voltage level is 10 kV to 15 kV, and it is improved or it is stepped off to around 400 kV, right, or 220 kV, like that, in case of Indian scenario I am talking about. So this is the function of generator transformer, which is a step up transformer generally, and it is used in the generating substation to step up the voltage from very low voltage like 10 to 15 kV to 400 kV, 220 kV or 400 kV. And another one is your power transformer, which is used for in case of interconnecting substations, right? In the interconnecting substations they are used, so they are called the power transformers. And then next is your distribution transformer, which is used in the distribution substation, right? Distribution substation. So the function of this is to step down the voltage, step down. This is a step down transformer, right? This is unlike the generator transformer, which is always a step up transformer, right? Generator transformer is your step up transformer, but in the distribution transformer is a step down transformer. Similarly, there are other transformers we call pole mounted lighting transformer. This is also a distribution transformer. This is generally used in case of low voltage distribution system, right? Distribution transformer used in low voltage network, right? And your next is your grounding transformer. It is used for grounding the neutral, okay, grounding neutrals. And next is your regulating transformer. So this in fact regulates the voltage, regulating transformer phase angle, right? There are many other transformers. Welding transformer used in case of welding machine, then your converter transformer, then instrument transformer. Already we talked about this, right? CT-PT for measurement and protection. CT it is used, CT and PT it is used, right? So this is for protection and measurement. Protection and measurement it is used, okay. They are called the instrument transformers, okay. Now let us consider here the protection of power and distribution transformers only, right? Power and distribution transformers only, not the other transformers, because there are many other transformers here you can see, but only we will consider here the power transformers and distribution. Also the generator transformer is one kind of power transformer, right? So let us see the phasor diagram for a three-phase transformer. So already we know the three-phase transformer, they can be three single-phase transformers connected together in different fashions, or it can be a single three-phase transformer in which all the three cores and three windings are installed inside a single unit, right? So nowadays, previously in the previous days, generally the single phase transformers are chosen and they are connected together to make a three-phase transformer bank. But nowadays, because of the advanced technology, so three-phase transformer in a single unit is coming or manufactured, and it is in use, right. Now if we'll see the block diagram of a 3-phase transformer, so it is a star delta transformer, right, and this is your supply side, which we call sometime primary side, right, primary side, and also this is your load side, which is sometimes called the secondary side in technical term, right. Already we know this in the Mason course, and both the side can be changed also. This side can be used as primary side, this can be used as secondary side. So it depends upon the use, right. So this is a star delta transformer where the primary side is connected in star fashion, right, you can see here, and the secondary side is connected in delta fashion, right. And here we will see the phase voltage and line voltage, they are different. The relationship already we know, right. So I can write the line voltage as √3 VPH phase voltage, right. Similarly, in case of delta side, I can write your line current as √3 phase current, right. So here we can see that these windings, the phase current in fact flowing in the windings, right, and in case of star connection, in case of primary side, in the star connection, the line current is equal to the phase current, right, okay, and here the phase voltage is equal to the line voltage. This is the difference of relationship between current and voltage. Already we know this, right. So now we'll see the phasor diagram for this because we are only concerned about the current, because current is our main concern in case of protection scheme. Therefore we'll talk about only the phasor diagram of current, right. So now we can see here. So the phase sequence is this, right. So therefore when I will draw IA here, then your IB will be 120 degree lagging. So this is 120 degree lagging, here it is IB, and your IC is 240 degree lagging. So it will be 240 degree lagging from IA, right. So now I can, sorry, this is your IC in fact, right. This is your, so this is your IA, IB and IC here, right. So now I will start from the primary side current. So primary side I have represented the current in the capital letter, and that is IA, and in case of secondary side I have represented in small letter. A is small, ABC are small letters, right. So now I can write here, this is your primary current IA, and this is your secondary current which will be induced in the secondary side. Similarly, your IB is primary side phase B current, and I small b is your secondary side phase B current. Similarly, your IC, capital C, is your primary side phase C current, and IC is your secondary side C phase current, right. Now if I will plot the line current in the secondary side, right. So in secondary side the line current, if I will see, so what is this? This current will be, obviously, first let us see how the currents will flow, because as per the dot convention, in the primary side when the current will enter the dot, in the secondary side the current will leave the dot, right. So therefore here the current in the secondary side is leaving the dot, and in the primary side it is entering the dot. IA, IB and IC, they are marked, they are represented, and similarly in the secondary side IA, IB, IC, they are leaving the dot, right. Now if I will see, here it is connected to IC. Now if we will see the direction, this is your IA, right, this is your IA, and your current IC is flowing in this direction. I will write it as IC. Now the net current going out of this network is IA minus IC, okay. Okay. Similarly, in the line current in the phase B will be IB minus IA in this line, and again in the third line it will be IC minus IB. You can see this very easily, right? Now, if I want to plot these line currents, so how I will plot this? Obviously, your IA is there and I want IA minus IC. So, IC minus IC will be here somewhere, it will be here, right, somewhere here it will be minus IC, because IC is here, so it will be minus IC. So, IA minus IC will be the net current here, that will give me secondary line current, right. Okay. So, now if we will compare the line current of the primary side and the line current in the secondary side, so what we will observe that line current in the primary side and line current in the secondary side. Let us see. So, line current in the primary side is this IA, right. This is equal to your line current, and that is equal to also the phase current, because it is in the star connected fashion. So, this is also equal to the phase current. So, now the line current, the phase difference between the line current in the primary side and the secondary side is 30 degree, right. Okay. So, this plays in fact an important role when designing the differential relay for 3-phase transformers. Similarly, if we will see phase B, the line current of phase B in the secondary side and the primary side, it also have a phase difference of 30 degree. Similarly, for phase C also it has a phase difference of 30 degree, right. That means your secondary line current is leading, it is lagging the primary line current by 30 degree, right. Sometime also therefore it is known as 30 degree connection, right, 30 degree connection in 3-phase transformer. So, this is a star delta connection, right, star delta connection is known as 30 degree connection. Similarly, delta star connection also known as 30 degree connection, but in that case your current will lead, right. So, here the 30 degree, it is 30 degree lagging connection, and in this case it will be 30 degree leading connection. You can see it by doing yourself, right. Now, you can draw the phasor diagram for 3-phase delta Y transformer yourself, you can try it. Okay. So, now let us see the equivalent circuit of the transformer, and we will see using the equivalent circuit the fault current, how the fault current is determined. So, this is already we know, this is your primary side, this is your secondary side, and the number of turns are N1 and N2. And now, by drawing the equivalent circuit, so your primary side equivalent parameters are R1, L1, they are representing the resistance of the winding and the leakage inductance of the winding. Similarly, your secondary side, one is R2 and L2. So, R2 represents the winding resistance at the secondary side, and L2 is your leakage inductance at the secondary side. And there are two more important parameters, they are called the magnetizing branch parameters. So, one is Lm and Rm. So, Rm is your resistance. So, this in fact represents the core loss component of the transformer, right. Resistance representing the core loss component, which is parallel to Lm, which is the magnetizing inductance, right, of the transformer. Now, this part is your ideal transformer, right, whatever voltage is here, just it will replicate based on the transformer turns ratio, right. So, now this is your equivalent circuit, and what will be your fault current? If we will see, in fact your series impedances, they play a very important role in case of in case we are trying to determine the fault current, right. So, your fault current in fact it will be V by Z series, rather than we say, because Z shunt is very high, okay, this is very high value, right. So, your voltage is 1 per unit, whereas your jet shunt is 20 per unit. So the current flowing through this will be 1 by 20 per unit, right? So that means it will be very less as compared to the current flowing through this branch. This current will be your I fault, that is equal to 1 by 0.08 per unit, right? So this is in fact large value, and it is equal to 12.5 per unit. So therefore approximately the fault current we say is 1 by Z series, okay, and it is equal to 1 by 0.08 per unit. So that is nothing but equal to approximately equal to 12.5 per unit, as we are neglecting the current flowing through the shunt branches because the value of the shunt impedance is very high, okay. So now we will see the type of various types of faults in the transformer. What are the various faults in fact existing in case of transformer? Let us see this, and then we will go for the protection scheme. So what are the various types of faults? So transformers are subject to a variety of faults. The most common fault being the winding to core fault, right? This is the most common fault, and it happens because of the weakening of the insulation, right? So as the insulation becomes weak, so therefore your winding to core fault most of the time happens. Then phase faults inside the transformer are very rare, because phase to phase fault, it is very rare in case of inside the transformer. However, such faults may take place outside the transformer. That happens on the transformer terminals, which fall within the transformer protection zone as well. So when the differential protection is differential protection scheme is implemented at both the sides of the transformer, so in fact even the fault happens at the terminal, it lies inside the protection zone, right? Okay, as mentioned here. The power and distribution transformers are generally provided with online tap changing gear, and this is another major source of fault. So because of this online tap changer, most of the time the fault happens at the terminal of the transformer. So all large transformers are of oil immersed type. There is a possibility of low level of oil due to leakage. So in such cases an alarm must be raised. We will talk about in detail, more detail about this, and the transformer may eventually have to shut down, okay. And another peculiarity of the transformers is that they experience large inrush currents at the time of switching. During switching phenomena, it experiences large inrush current. It is because of the magnetization effect. So they happen due to because if they happen to be unloaded, right? So under no load condition it happens. This is neither an abnormal condition nor a fault as far as the transformer is concerned. So inrush current needs special attention. Under no load condition, generally this inrush current phenomena happens because of the switching, right? So this inrush current needs special attention while designing the protection of transformer. So therefore there are special protection schemes for detecting this inrush current. So transformer may develop interturn faults, giving rise to hot spots within the winding. So this interturn fault generally, as this is seen from the terminal, such as interturn faults may not cause appreciable current. Generally these interturn faults, it doesn't actually cause appreciable current. Therefore the relay doesn't detect the overcurrent relay. Even if it is there, it doesn't detect this interturn fault, and it is in fact very difficult to detect by electrical means. So therefore there are some non-electrical methods used to detect this interturn fault. We will talk about this in the future classes. The transformers may suffer from overfluxing. We will talk about this in more detail. Also called overexcitation due to under frequency operation, because we know that it is voltage is directly proportional to your phi and f, right. So your phi will be directly proportional to E by f. So that means your phi is inversely proportional to 1 by f. So as your frequency will go down, your flux will your frequency will go down, your flux will increase, right. So therefore during the under frequency operation at rated voltage overfluxing phenomena happens. And overfluxing may also be caused when the transformer is subjected to overvoltage at rated frequency. As we can see here, your flux is also directly proportional to V, right. So this E, or you can say E. So therefore it is directly proportional to E when your F is constant, rated frequency. Since large transformers usually operate at their design limits, overfluxing can be dangerous and needs immediate protection. So overfluxing means as soon as the overfluxing phenomena happens, your transformer core gets saturated, right, and leading to abnormal operation. Transformer core becomes saturated. Okay. So this can be avoided only when if we can have a very high cross section area, high cross section core, right, cross section core. But high cross section core cannot be possible, it cannot be possible to implement this because of the design limit, right. So therefore most of the time, because of the overfluxing, this transformer core becomes gets saturated. Now let us see the overcurrent protection for the transformer. So as we can see here, already we have talked about the implementation of overcurrent schemes, overcurrent protection in a three-phase feeder, right. We generally put two overcurrent relays in phase, and another relay, that is because the relay has three-phase winding. So these two phases will be connected to two phases and other phase will be connected to the ground fault, right. So therefore, and these three relays in fact combinedly gives the full protection to the distribution feeder. So here also similarly for the transformer protection, these two relays in fact detects the phase faults and one is there to detect the ground fault. So here therefore your transformer is being protected, and generally this overcurrent protection is used, overcurrent protection scheme is used as backup protection, right. Most of the time it is used as backup protection, and your differential scheme is used as the primary protection. Such a scheme may serve the purpose of providing either the primary protection for smaller transformers. For smaller transformers, it acts as the primary protection, or the backup protection for the bigger transformers. So for bigger transformer, it acts as a backup protection, because for bigger transformer the differential scheme acts as the primary protection. The pickup value of the phase fault overcurrent units is set such that they do not pick up on maximum permissible overload, but are sensitive enough to pick up on the smallest phase faults. So the pickup of the earth fault relay on the other hand is independent of the loading of the transformer. Even the load becomes sometime unbalanced, under that condition your earth fault relay should not operate. The neutral current under the load condition is quite small, The neutral current is essentially existing because of the load unbalance. So it should not trip under that load unbalance condition. It only should detect the earth faults or ground faults. Okay, so let us see now the percentage differential protection of all of transformers. How we can implement a differential protection scheme in a transformer. So here a delta star transformer with neutral grounded is considered. Here the primary side of the transformer is connected in delta fashion, as we can see here, and the secondary side is connected in the star fashion. This is your star point where all the one side of the transformer is connected together and other side is connected to the load somehow, right. Now we have CTs at both the sides, and the CTs are, in fact, we cannot fix the CT in the winding itself, because CT cannot be fixed in the winding. It should be fixed in the line. So therefore in the line the CTs are being fixed. So therefore 3 CTs are connected in the 3 phases of the primary side, and another set of 3 CTs are connected at the secondary side, 3 phases of the secondary side, right. Now if we will see, now the question is how these CTs should be connected so that your under normal operating condition your relay should not trip, and under abnormal operating condition, that is the fault within this zone of protection or internal fault, it will trip over the relay in the spill path. However, it should not respond to the normal load condition and the external fault to this transformer, right. So let us see this. So let us first decide the CT ratios. If the transformer ratio is given somehow, if the transformer primary to secondary turns ratio is given, T is to 1, and the CT is connected at primary is having current ratio N is to 1, then what would be the current ratio of CT is connected at the secondary side? If the primary side the ratio is N is to 1, and what will be the turns ratio in the secondary side if your transformer ratio is T is to 1? Okay. So how will find this? You can find this using simple formulation. So your secondary current, if your transformer ratio is T is to 1, so your secondary current I can write IA, I small a is equal to T times I capital A, and hence I can write IA CT, that is the primary side CT secondary current will be equal to IA by N. It is because of the turns ratio in the CT. And now if I can write the secondary side CT current, the CT secondary current at the secondary side, that will be IA CT, that should be in fact equal to IA by N, so that your spill current will be 0, right. So therefore I can write it under normal operating condition, and that I can write in fact equal to T into IA. So just I am writing T both the sides, both numerator and denominator I am multiplying T, right, and then T into IA capital T I capital A is equal to nothing but I small a divided by T dot N, T into N. So therefore I can say that the CT ratio at the secondary side will be T into N, right. So this is how we can determine the CT ratio in the secondary side. So presently let us assume that for simplicity T equal to N equal to 1, okay. By assuming this, how can I connect these transformers, these CTs, for a delta star transformer? For a delta star connected transformer, how can I connect these CTs? In what fashion I should connect the CTs? So in this figure you can see here, this is a delta star transformer, and your CTs are connected in the delta side it is connected in star fashion, and in the star side it is connected in delta fashion, so that your current through the spill current will become 0. How it will become 0? Let us assume that, let us say the transformer ratio is equal to T:1, and your CT ratio at the primary side is N:1, and the CT ratio at the secondary side will be, obviously it will be Tn, right? Okay. So now the current flowing through this, here it will be Ia by Ia minus Ic, because we considered n equal to 1, so therefore it is mentioned here Ia minus Ic. So let us now consider in terms of T and n. So it will become Ia minus Ic by n, right? And here in this path the current will be obviously Ia minus Ic by Tn, right? So Ia minus Ic will convert to the primary side current, so it will be nothing but equal to Ia minus Ic into T by Tn. So it will get cancelled and it will become Ia minus Ic by n, so which is equal, right? So here the current is coming here Ia minus Ic, and the current flowing here is Ia, capital Ia minus Ic. So therefore the current in the spill path will be 0, right? So therefore we should remember this thumb rule, that in the delta side the CTs are connected in the star fashion, and in the star side the CTs are connected in the delta fashion, right? So in the delta side the CT connection is star, okay, and in the star side your CT connection is delta, okay. This is your thumb rule, and then your design is perfect. Okay, so now let us see one external fault that is happening from phase C to ground. Then what will happen to your scheme? So for this external fault we can see here that this is your fault current IC, and in fact this fault current will have impact in the primary side and in the primary side of the transformer. Therefore therefore the current in the CT also change based on the reflection of the secondary side current in the primary side. So therefore here the current will become IC minus IB, and here also become IC minus IB, and in the second line it will become IB minus IA, in the second line it will be IB minus IA. So here n equal to T equal to 1 is assumed, right? The CT ratio and the transformer ratio is assumed equal to 1. So IA minus IC, and here also it will be IA minus IC. So therefore the spill current will be 0 for all the three cases. Now you can see the spill current is 0 for the external fault, right? So therefore to the external fault, this kind of implementation of CTs, that is in the delta side the CTs are connected in the star fashion, and in the star side it is in delta fashion. This is in fact working very nicely in case of external fault as well. So let us consider an internal fault. So how it will respond to internal fault? So if the internal fault happens here, a metallic fault, let us say the bolted fault, right? So for a bolted fault here your IC will become 0, right? Now what will happen because this will be reflected here in the primary side, and here in the CT the current will be IC minus IB, right? And now this IC minus IB will be here, and what will be the current in this line? So the current through this is, what is this current? This current is IC minus IB, but here in this branch as IC is equal to 0, so this will become 0. So only minus IB will flow here, right? So as minus IB will flow, so there will be a spill current, that is equal to IC, right. So therefore the spill current here is IC, and again another spill current here will be minus IC, because here in this branch only IA is flowing, right. You can see here, because IC is 0, so only IA is flowing. So therefore here the spill current is minus IC, and therefore to the internal fault this kind of scheme will very well, it will respond very nicely. Now let us consider the arcing fault. Okay. So in case of arcing fault, what will happen? Let us see. So let us see the arcing fault. Arcing fault, in fact, when the arcing fault happens here at terminal C, so your IC will not become completely 0. It will in fact has some value. It will be lesser than capital IC, right. So it will be lesser than the capital IC. So therefore if we will see here, it will become the spill current here will be IC minus I capital C minus I small c, and similarly here in the third line it will be minus of I capital C minus I small c, right. So therefore this will also respond to the arcing fault as well, right. So that means to the internal fault, whether it is a bolted fault or an arcing fault, it does not matter. So this will respond very nicely to the internal fault, and it will not respond to the external fault. So now we can stop here. In the next class we will talk more about the differential protection scheme implementation in the transformer, and we will see through an example how we can implement in the transformer. So thank you very much. Thanks a lot for your kind attention. Thank you.